Analysis of variance, or in shorthand, ANOVA. So, Anova. Okay, so it's just some of the places that we have been, right, in these PowerPoint journey we've taken is descriptive statistics. The very, very beginning part where we just kind of organized and simplified the data. We talked about histograms and polygons and bar graphs, things like that. Some of the inferential statistics that we've covered is, of course, all the t-testing, whether it be a single sample t-test or independent or any of the kind of matched or related sample t-testing. And then where we're going, so of course, this one is Anova, so analysis of variance. And then the last two PowerPoints will cover correlation and / regression, and then chi-square. So analysis of variance. This is a hypothesis testing procedure, so you're still going to go through that same 4-step hypothesis series, right, of setting your alpha and finding the critical region, that kind of stuff. But now what we're doing is we're actually shifting. So with t-testing, we're limited to 2 conditions, either a pre or post-test or a matched sample. You're comparing 2 different groups, right? With analysis of variance, or ANOVA, you have more flexibility in designing your experiments, interpreting your results, finding out which one of the groups, vary differently. So we're not going to be limited to just having 2 conditions. Okay, so again, with an independent t-test, we're evaluating 2 groups that are independent from one another. So an example might sound something like, well, a sample of individuals who receive treatment for anxiety compared to a separate sample of individuals who receive no treatment for their anxiety. And then we're going to test them after and see there's a difference there, right? And then with a related sample t-test, you're looking at the relation between 2 groups, so either a sample or a matched sample, so repeated or matched, right? And so this might look like a sample of individuals are tested on memory performance before 6 weeks of cognitive exercises, and then again after they have those cognitive exercises. And we're going to see, is there a difference in that score? So a typical situation where ANOVA would be used is anytime that you have more than 2 populations that you're pulling from. So in this case, we have 3 populations that we're pulling from. So in population 1, we're going to pull, pull 15 people for each one of the groups, right? But the mean for the first group had a 23.1 compared to 28.5 for the second group and a 20.8 for the third group. Sum of squares also vary too. So 114 for the first group, sum of squares 130 for the second group, and then 101 for the third group. So again, the individual numbers are going to vary. Okay, so let's do an example here. So researchers are examining driving performance under 3 different cell phone conditions. Driving with no cell phone, like no phone in the car at all, right? Talking on a hands-free cell phone, like a Bluetooth or something like that, and talking on a handheld cell phone. So they're actually going to hold, dedicate one hand holding it next up to their face as they talk. All right, let's get some terminology out of the way. So a factor, in this case, the independent or quasi-independent variable that designates the groups being compared. So we're going to be using a quasi-independent or a non-manipulated variable, and our factor is the cell phone condition, right? Handheld, hands-free, or no cell phone. The level is their driving performance. How well do they drive? Like on a scale from 1 to 10, they scored a 7 or a 3, right? So these are individual conditions or values that make up that factor. And the factorial design is just a study that combines 2 or more factors. So sometimes you're going to hear analysis of variance or ANOVA described as a factorial design. The null hypothesis. It sounds something like mu1 equals mu2 equals mu3 equals mu4, right? Or you can just simply say the population mean for all the conditions are the same. Or in other words, if the population, or in the population, the means of the groups don't differ, from each other. Alternative hypothesis, well, you have a couple different ways you can say it. One, that there's at least one mean difference among the population that's different, right? Or you can, all the means could be different, right? Or some means are different, but others are not. And with our F, and so with the T, we use a symbol of, with the t-testing we use T, with z-testing we use Z, with ANOVA we're going to use F. So our F-test, or the statistic that we get with ANOVA, doesn't give us specifics about where the differences exist. It just gives us an omnibus hypothesis, meaning that one of these are different. You have to run a post-hoc test afterwards to find out which one is the one that's specifically different. Okay, so your F equation is, F is actually like a t squared. So F is always going to be positive. F or Anova distributions are always positively skewed, right? So it's the variance or the differences between the sample means divided by the variance or the differences expected with no treatment effect. Okay, and it's not possible to compute a sample mean differences between more than two samples. So what we're doing is we're actually it's more based on like variance, right, differences, instead of the sample mean difference. The numerator, the top part of that F equation, is going to measure the size, the differences among the sample means. The denominator, the bottom part of that F ratio or F equation, right, measures the mean differences that would be expected, again, if there's no treatment effect or if that null hypothesis would be true. Okay, so you have a couple different treatment that you're looking at. You're looking at between and within, right? So between treatment variance is the variability that results from the general differences between the treatment conditions. Okay? And the variance between the treatment conditions measures the differences among those sample means versus the within treatment variance, or the variability within each sample. And I do have a whole video that's titled Between and Within Treatments, and it explains this a little bit better with using your own sibling set versus your sibling set compared to your cousin sets. So make sure you watch that video too. So the within treatment variance is the variability within each sample, and between is that variability between the sample groups. Okay, there are systematic differences caused by differences, and that's what you're actually looking for whenever you're looking at that variability between treatments. You're looking at, did the medicine work? Was the therapy effective? And then you also have these random unsystematic differences, right? There's individual differences, or in some cases, experimental/researcher, error. There's not usually systematic differences related to treatment groups that occur within the group. If there are, there's random unsystematic differences, right? Because you're not trying to see the differences between that one group. You're really, or within that group, you're trying to look more so between the groups. Okay. So F ratio, right? If the null hypothesis is true, the size of the treatment effect is near zero. And F, again, F is our symbol that we're going to use for Anova, is near 1. The size of the treatment, the alternative hypothesis would then be the size of the treatment effect is greater than 0. And F is noticeably larger than 1. It's not going to be like, oh, 1.1, is that, no, it's going to be like 13, 47. It's going to be noticeably larger than 1. The denominator, the bottom part of that F ratio is called the error term. And again, it's trying to measure the variance from these random unsystematic differences. Okay, some of the assumptions. Again, homogeneity variance. You have to make sure that homogeneity variance is met, and you can do that with your F max table. The observations within each sample are independent, right? So you can't double dip, right? The populations from which samples are taken from are normally distributed. And of course, that homogeneity of variance assumption has to be met. Some symbols that we're going to use is one is K, the number of groups / treatment conditions, right? NK, the number of subjects in each group, right? Sum of squares total, and normally we don't write sum of squares total, we write SST for the sum of squares for the total study, SSW for the sum of squares for within groups, and SSB, like boy, for sum of squares for between group variance. And so we don't actually write out the whole word between, we just go SSB. All right, K. K is the number of groups / treatment conditions. So in our sample study here, we're going to do remember the no cell phone at all, the handheld cell phone, and then the hands-free cell phone. So K for us equals 3. And we have 5 people in each group. So NK is, N for the first group is 5, and for the second group is 5 again, and then 5 again for the N for the third group. Now, big N is still 15, right? Or if you just add up all the little n's, 5 plus 5 plus 5. You don't have to necessarily have equal sample sizes, but in this example, I'm using equal sample sizes. Okay, T, or TK, the sum of scores in each condition. So I just have a little bit of the data here. I just kind of chopped it off. I'm not using the whole data set quite yet. So again, we have no cell phone. So say on a scale from 1 to 10, right? One person scored a score of 4. One person in that group scored a score of 6. I know I said we had 5 people in the study, but I'm just chopping it off and just using 2 right now. In the handheld cell phone, on a scale from 1 to 10, one person scored a 2 and one person scored a 1. So what we're looking at right here are raw scores, right? T is when we total up those raw scores, right? So T, or the total amount for column 1 or group 1, is 10, 3, and 2. Okay, so again, just keep in mind that those little numbers there are the raw scores for driving performance. G, or sum of T, and in some textbooks, you're going to see G for like grand total, where you're just going to add up all the T's. You're going to find the total for the group 1, total for the group 2, total for the group 3. You're going to get your grand total. I've seen it G, and I've also seen it sum of T. Either one works. Okay, and again, we're going to have SST as the sum of squares for the total study, SSW for the sum of squares for within, and SSB for the sum of squares for variance. Between. Okay, so MS is the mean square, which is like Anova's word or Anova's symbol for variance. So before we use like variance, it's like the little S with a 2 on top, or the little O with a curly hat part with a 2 on top, right? MS is Anova's variance. Okay, here's all the data. Okay, so we have again a no cell phone right here in this column, right? And again, we have 5 people, right? We have one person who scored a 4, and then a 3, and a 6, and a 3, and a 4. So our total for this column is 20. And I'm going to do that for each one of the groups. Again, I have 5 and 5. I'm going to add up the raw scores, 0, 1, 3, 1, 0. Gives me a raw score total of 5, right? And then mean, averages, right? So just add them up. So add your 20 divided by your 5, and you get 4. Get your add up to your 5, divide by 5, you get 1. 5 and 5 and 1 again. Sum of squares, you use your sum of squares equation for each one of those, right? So, and then G, or sum of T, is you're going to add up your 20 and your 5 and your 1 again. And big N is your total number of people in the study. Sum of G squared, or sum of T squared, would be just adding up all the T squares, right? Or all the raw scores squared. Okay, so what you're going to do here is you're going to find your sum of squares total, and I'm going to show you the equation for sum of squares total, sum of squares between, and sum of squares within. Now, do keep in mind that once you have sum of squares between and sum of squares within, you can find sum of squares total. You just add between and within together. Or if you have sum of squares total and you know sum of squares within, you can find sum of squares between, because you just take sum of squares total, you minus sum of squares within, and voila, you get sum of squares between. Okay. So the equation, I'll show you the equation for all of them though. The equation for sum of squares total is the sum of T squared minus sum of T squared divided by N, and in this case, big N, so for us 15, right? So 106 minus 30 squared divided by 15 equals 106 minus 60. So we have our sum of squares total as 46. Again, I did color code it. Hopefully that helps you find out where I'm getting all these numbers. Sum of squares within is sum of squares for the first group plus the sum of squares for the second group plus the sum of squares for the fourth group. Right, so in our case, 6 plus 6 plus 4, 16. Sum of squares between is the trickiest one, in my opinion. Maybe not for you, though. Okay, so what you're trying to do is you're trying to find the sum of all the mean scores squared, right, minus the total sum of the mean squares divided by n of the means, okay, or the average mean for each group. Okay, so again, I color coded it. So this first part here, this sum of mean square, right? So I have mean for the first one is 4, so I go 4 squared. Mean for the second one is 1, 1 squared. Mean for the third one is 1, 1 squared, right? So I'm going to square each one of these, so 16 plus 1 plus 1, right? Minus this whole amount here. So just the 4 plus 1 plus 1. That number squared, so 6 squared, so 36, right, divided by 3. So you're going to go 18 minus 12 is 6. Okay. And then once you have the sum of squares means, you can then throw it into your sum of squares between, right? And it's just n times sum of squares mean, 6, right? So 5 times 6 is 30. And again, sum of squares total equals sum of squares within plus sum of squares between. Okay, so we have a Anova summary table here. It does look long, and it is long whenever you write out on a piece of paper, but it does keep all the bits in order. Okay, so again, we have sum of squares between at 30. We have sum of squares within at 16, which gives us a sum of squares total of 46. This is where degrees of freedom start getting really crazy. Okay, degrees of freedom for your, so DFB, so your degrees of freedom between, is K minus 1. Okay, degrees of freedom within is N big N minus K, and degrees of freedom total is N big N minus 1. All right, let's keep going. So, we had 3, so 3 minus 1 is 2, and you're going to keep going through all that. And you need to know these because this is going to help you find your F crit, or your critical value for that Anova, right? So again, how we did with Z crit versus Z obtained, and T crit versus T obtained, we're going to do F crit versus F obtained. Okay, variance again is this MS, right, or this variance for Anova. And variance between is SS between divided by DF between. In this case, gives you 15. Variance for within is SS within divided by DF within. In this case, 16 divided by 2. Okay. And then for your F obtained formula, for your F statistic, right, you have your variance between divided by your variance within. So in our case here, we had an F obtained of 11.28. We look at our F, or our Anova table, and in the Graviter text is B4, and Aaron, we have a different table, but usually they're at the end of all the textbooks. You have your tables. You can also find these online. Okay, so we're going to set them at, set our alpha at 0.052 tail, and we're going to find the critical value of F. Okay, so DFB, so K minus 1, 2 in the numerator, and DFW, 12 in the denominator. Okay, so I have a whole video that shows you how to use the F table, or your Anova table, to find your critical value of F. So please, please, please watch that video and learn how to find your F crit. But for our sample here, we have F crit equaling 3.88, and we compare that F crit of 3.88 to our F obtained of 11.28, and we can know that we reject the null. Okay, how you would write it in an APA style looks something like this, right? And so I'm going to read it, and I'm going to have you read along with your eyes and see if you can understand what I'm saying. So you can tell that the researcher ran an Anova, analysis of variance, and they had 3 groups, right? And they had 15 people total in their study with the F obtained statistic of 11.28. And because the P is less than 0.05, they rejected that null hypothesis with an alpha set at 0.05. Power. Power varies with the sample size, right? As sample size increases, power also increases. If you want to think of it like if you have a medicine or a therapy and you test it on 100 people, is that powerful? Sure. What if you test it on 1,000 people and it still works? Is that more powerful? Absolutely. What about 10,000 people? You see how as you increase that sample size, the power also increases? And power also varies directly with the size of the real effect of the independent variable. And think back to chapter 1. Independent variable is that variable that the researcher manipulates. Okay, the amount of medicine somebody's getting, the lack of sleep if you're looking at sleep deprivation, that type of stuff. So the greater the real effect, the greater the power of the analysis. And then power varies inversely, though, with sample variability, right? If sample variability is all over the place, if your scores are just scattered, some are really high and some are really low, the lower your power is. Effect size. So far you have learned how to find Cohen's d, estimated Cohen's d, percentage of variance accounted for, and now I'm going to introduce Etta. This is what she looks like. So it's like a little beautiful N, right? And her name is Etta squared. And again, this is trying to compute the variance, or the percentage of the variance accounted for by that treatment condition. In our case, what kind of cell phone condition were they driving under? It's the same concept of R squared. Okay, so it's the SS between divided by the SS total. And that's going to give you your eta squared. And you usually just put that at the end of your research or results section. Again, Anova compares all individual mean differences simultaneously in one test. And because it's doing it all at one time, it doesn't really tell you which one of the samples is different or statistically significantly different from the others. So you have to run a post-hoc test. And I have another video that shows you how to run a post-hoc test to determine which of the mean differences is the one that is statistically significantly different and which ones are not different. A post-hoc test compared two individual means at one time. So it's also called a pairwise comparison. So you're not going to run it all the same. You're going to compare driving condition A with driving condition B. And you're going to get a number. And then you're going to compare driving condition A with driving condition C. You get a different number. You're going to do with B and C, right? You're going to do each one of them only on a pair. Okay? And what happens though is if you did that all at one time, you would create this really high risk of type 1 error, right? So increasing the number of hypothesis tests also increases the probability of committing a type 1 error. So you want to keep it as small for factors as possible. Okay, true or false. Post-hoc tests are needed if the decision from an analysis of variance is to fail to reject the null hypothesis. And number 2, a report shows Anova results of Anova 2 and 27 equaling 5.36, p less than 5.05. You can conclude that this study used a total of 30 participants. So take a second and go through that and then come back. Okay. False and true. So post-hoc tests are only needed when at least one of the mean differences is significant. Again, the post-hoc test responsibility in life is to find out which one of the mean samples are different. If the Anova comes back and says, nope, they're pretty much all the same, you don't have to run a post-hoc test at all. And so, because degrees of freedom between 2 equals k equals 1, and degrees of freedom within 27, n equals, or n minus k. Okay. Again, as always, do your homework. Don't be late on that, and then email me or text me with any questions. Thank you.